Good day, viewers. Today we are going to be solving another problem under thermodynamic relation. And so what we have here on the board says find the value of the coefficient of volume expansion B, beta, and isothermal compressibility K for a van der Waals gas obeying this relation. Now this relation is the relation or the mathematical expression of van der Waals gas. Now what we are going to be doing is that we are going to be making P, which is pressure, subject of this relation. So if we do that, we are going to be having P, the bracket of P plus A all over V square into the bracket of V minus B equals to RT. Now we want to make P the subject of the formula. What we do first is that we divide both sides of this equation by V, by the bracket of V minus B. So we divide by V minus B and also by V minus B. And so V minus B, we go with this V minus B. And so what we have here is P plus A all over V square will be equal to RT over V minus B. So this is what we have. So next, we can take A over V square to this side. So we have P is equal to RT all over V minus B. Taking A over V square to this side, it becomes negative. So we have A all over V square, which is negative. So now we know that from cyclic relation in our previous videos, we have what we call cyclic relations. You can check our previous video on the derivation of cyclic relation. So cyclic relation here says that the V all over the T, keeping P constant, the T all over the P, and we also have the P all over the V, keeping T constant. So we have keeping P constant and keeping V constant. Minus 1. So this is what we have. So now we also know that B, which is beta, is equals to 1. So we know that beta, which is the coefficient of volume expansion, is equal to 1 over V, the V all over the T, keeping P constant. And so from the question, we were asked to find the value of the coefficient of the volume expansion B and the isothermal compressibility K for a van der Waals gas. And so we need to find a relation that will relate this with our cyclic relation. So the first thing we do is that, having known this cyclic relation from our previous videos, which has been proven, we then make the partial derivative of V over that of T, keeping P constant, the subject of the formula here. If we do that, we have the V all over the T, keeping P constant, will be equal to minus 1, the T by the P, V, the P over the V, T constant. So this is what we have. So if we simplify further, we are going to have the V all over the T, keeping P constant, will be equal to minus the T all over the P, keeping now to ensure that the T over the P, keeping V constant, goes up. What we do is that we are going to take the inverse, which is the P, the V all over the T, keeping pressure constant, will be equal to minus the P all over the T all over the P all over the V, keeping temperature constant, keeping volume constant. Now what we have here, we have the V all over the T, keeping pressure constant, equals to this equation. And we also know that the V over the T, keeping pressure constant, multiplied by 1 over volume is equals to our coefficient of volume expansion. So next, what we are going to be doing is that we are going to be substituting the value of the V all over T, keeping P constant in this equation. It implies that beta will be equal to 1 all over V, the value of the V over the T of P, which is this, minus the P all over the T of V all over the P all over the T of T. Similarly, we know that K, which is our compressibility factor, is equals to minus 1 all over V, the V all over the P, keeping temperature constant. This is our compressibility factor. It implies that what we have here is the V all over the P, keeping temperature constant. So now, from van der Waals forces, we know that if we make from here, if we differentiate with respect to T, we are going to have, we can call this equation 1. So if we differentiate equation 1 with respect to T, we are going to have the P all over the T at this point will be equals to R all over V minus B. This now becomes a constant and is equals to 0. So this is what we have. So what we are going to do here, now this is what we have. So what it means is that we have the P all over the T of V, keeping V constant, is equals to R over V minus B. So similarly, from this equation, we can decide to differentiate with respect to V. If we differentiate with respect to V, so what we just did here is that we differentiated the van der Waals force equation with respect to T. So that's what we did here. So we have this. We can just say with respect to T. The van der Waals equation with respect to T. So next, we are going to be differentiating this same equation with respect to V. So if we differentiate this equation with respect to V, we are differentiate this equation with respect to V by applying quotient rule. We are going to have the P all over the V, temperature is kept constant, will be equals to RT over V minus B all squared minus 2A all over V cubed. So we have just differentiated this equation with respect to V, and this is what we have. So next, we are going to be looking at this both equation now. From here, we know that the compressibility factor K. So what we have just done, like I said earlier, we have just differentiated this with respect to V. This is what we have. Now we know that our compressibility factor K is equals to minus 1 over V, the V over the P of T. Now we can take the inverse of this equation. If we take the inverse of this equation, we have the V all over T all over the P, keeping T constant, which will be this. And then we can now substitute the resultant result into this equation. So if we do that, so what we have here is P over the V of T equals to RT all over v minus b squared minus 2a over v cubed. So now we are going to be taking the inverse of this equation. So if we take the inverse of this equation, it implies that the t, or the v rather, all over the p so we have the v all over the p, keeping t constant, will be equal to 1 all over rt all over v minus b all squared minus 2a all over b cubed. Okay, so we have just taken the inverse of the p all over the v, keeping t constant. So when we take the inverse, we have the v all over the p, keeping t constant. Instead of the p over the v, we have the v over the p. But for this place, we are going to be having 1 all over rt all over v, the bracket of v minus b all squared minus 2a all over v cubed. So next, if you look at this relation, we have beta to be equals to 1 all over v. So now we have the p over the t keeping v constant. We have the p all over the t keeping t constant. And here you can see that we have the v all over the p keeping t constant, and we have the p all over the v keeping t constant. So here there's a little error here. It's supposed to be the v. So this is what we have. So here we have the p all over the v keeping t constant. Similarly, we have the p over the v keeping t constant. And here we have the p all over the t keeping v constant. So we are going to substitute the value of this for this, and we are going to substitute the value of this for this. So it implies that beta, which is the coefficient of our volume expansion, is equal to 1 over v into minus the p over the t keeping v constant. And the p over the t keeping v constant is equals to this. So we can just write r all over v minus b. So this is what we have. So similarly, we are going to be substituting the p all over the v, keeping t constant here, because the p over the v over the p all over the v of t, the p all over the v of t is this. And so we are going to be substituting it in that equation. So it means that we have all over rt all over v minus b all squared minus 2a all over v cubed. So this is what we have. So it implies that beta will be equal to 1 over v minus r all over c all over the bracket of v minus b all over rt over v minus b all squared minus 2a over v. So this is what we have. So similarly, we are going to be substituting the value of the v all over the p, keeping t constant for this. So we are going to be doing that right away. So now we are going to be substituting the value of the v over the p, keeping t constant, which is this in this equation. So it implies that k, which is the compressibility factor, will be equal to minus 1 all over v, the bracket of 1 all over rt v minus b or squared minus 2a over b cubed. So it implies that the value of our coefficient of volume expansion beta is this, and the value for our compressibility factor K is this. So it means that for a van der Waals gas that is obeying this relation, this is the value of the volume expansion, and this is the value for the compressibility factor. Thank you for watching.